Hello and welcome to the 13th session of the Introductory Biostatistics Distance Learning course. Today we'll be talking about the bootstrap and permutation tests. These are topics which are usually not covered in standard introductory biostatistics courses, but they are very useful modern techniques in statistics that you'll see if you continue your biostatistics education. And they're useful in practice, so I think that they're topics worth discussing, and they do provide some insight, so worth discussing here. So what is the bootstrap? So if you think back to our discussion of confidence intervals, whenever we had a confidence interval, so far we've just developed confidence intervals for the mean, but in order to place a confidence interval around the mean, we used the t-distribution. Remember, we had this general setup for confidence intervals, which was something to the effect of our estimate plus or minus a t-critical value times some estimate of the standard error. Okay, so that was our general format for confidence intervals. Okay, and so to do this, we had to assume that the underlying data were normal, right? In order to use this piece, the t-critical value, we assumed that the underlying data were normal, but that we just didn't know the population standard deviation. So what if we don't want to make this assumption, or we want to estimate a different statistic besides the mean? How can we calculate the variability in the estimated mean and the confidence interval? Okay, so how do we get this piece, the standard error? Well, one way to do it is to resample the data, resample the existing data we have using the bootstrap. Okay, so remember, for the mean, we had this cool result of sigma over root n from the central limit theorem, which we had used. So what if we're trying to calculate the variability in something else, some statistic besides the mean, or something more complicated? We can use the bootstrap. So let's take a look at what exactly the bootstrap is. Okay. So remember the big picture idea of statistics. Somewhere out there, there's this population that we're interested in. And in this entire population, the population has these Greek parameters: mu, the population mean, sigma squared, the population variance, and so on. But since we can't sample the entire population, we instead just take small parts of it, and from that we get our sample. And in there we have our x bar, that's our estimate of the population mean, and we have our s squared, our estimate of the standard deviation. Okay, so we take a sample from the population and use it to estimate the population mean or other estimate of interest. Okay, so what would happen if we were to take repeated samples? So here's my sample 1. If I had another one, sample 2, then I would have another x bar. We could call that x bar sub 2. And then I'd have another estimate of the s squared sub 2, and so on. And I could just keep continuing that process until I had n samples. Right? Okay, so if we had repeated samples from a normal distribution, the distribution of the sample means, we know, would look like this. Whoops, sorry, that didn't come out very nicely. This is supposed to be, whoops, sorry, that didn't come out well. This is supposed to be sigma over root n. Is the variability around the population mean, okay? And this is the standard deviation of the repeated sample means, and we said this is called the standard error, right? And this was that cool result that we saw using that online website that showed us this result. Okay, so we take repeated samples from a normal distribution, and then the distribution of the sample means would look as we've shown here, right? So that's in our previous way of doing things. That was, here was sample 1, and then we get x bar sub 1, and then we take sample 2, and we get x bar sub 2, and then we keep going until we had x bar sub n. And then if we plotted those, they would have this shape here, this normal shape with the standard deviation being sigma over root n. Okay, so that's the case of repeated samples. But in real life, we only have one sample. Okay, so we need an estimate of the standard error from only one sample. Okay, and so we said at the beginning, if the standard deviation is known, the population standard deviation, and the underlying population is normal, we use the normal distribution. But when do we ever know the population standard deviation? We don't. So when the population standard deviation is unknown, and we're willing to assume that the underlying population is normal, we use the t-distribution, which is what we've been using throughout to construct confidence interval. Okay, so what if we're not in either of these situations? How can we then estimate the standard error? Okay, what if we're unwilling to assume that the underlying population is normal? That's where the concept of the bootstrap comes in. Okay, so for the bootstrap, rather than having repeated samples from the population to estimate the standard deviation of the sample mean, we instead take repeated samples with replacement from the data. Okay, so this is a key. We're going to define what this means, but it's key to know that when we do the bootstrap, we take repeated samples from the data that we have, repeated samples from the data with replacement. And I'll talk about what that means here in a second, but that's a key component, with replacement. Okay, we then use the data. Using this data, we can then estimate the distribution and standard error of a statistic without assuming a distribution, without assuming normality, which is what we've previously done. Okay, so what does this look like? So now we have a sample. Before, this was our population, right? But now it's a sample. And from the sample, we have x bar and things like that. And then we use the sample. We resample from the sample to get bootstrap 1. And from there, we can calculate x bar star, let's call it, 1. And then we can do it again. And we get bootstrap 2. And from there, we get x bar star sub 2, dot, dot, dot. And we can do this, say, b times. So the bth sample and x bar star sub b. Okay? So now what we're doing is we're resampling the data that we already have to get a set of estimates from the sample mean based on bootstrap samples. Okay? And when we say with replacement, we'll make that a bit more clear with an example. But the key is that this is repeated samples from the data with replacement. So in other words, suppose I have a sample that consists of 3 numbers, 1, 4, and 7. Okay, suppose that's my entire data set. If I'm sampling from that with replacement, suppose I choose the first number and it's 4. Then I put 4 back into the pot. It's not like, that's what we mean by with replacement. 4 is eligible to be chosen again. So I choose again, suppose I get 4 again, and then I get 7. So that would be my first Bootstrap sample of my data set. Okay? Then I could take another Bootstrap sample and I'll get 1, 1, and 7. Okay? So that's what with replacement means. Once I've selected 1 here, 1 is again eligible to be chosen. The alternative to sampling with replacement is, of course, sampling without replacement. And if we were to sample from this data set here without replacement, we would just end up with 1, 4, and 7 back again, right? Because I would choose one of them, say 7, then it would be gone because it's without replacement. So I only have 1 and 4 to choose from. So they say I choose 1, and then 4 is the only thing left to choose from, right? So doing Bootstrap samples without replacement doesn't make any sense because you just end up with your data set again. So the concept of the Bootstrap, we always sample with replacement, so we get different data sets from our original data set. Okay? And so once we do this b times, here's our first Bootstrap sample, here's our second Bootstrap sample, here's our bth Bootstrap sample. We now have a distribution of sample means, or whatever statistic we're interested in. We're just using the sample mean as an example. But it could be any sort of statistic that we're interested in. So now we have a distribution for that statistic. So the distribution of the Bootstrap samples is then used to estimate the standard error of the sample mean or other statistic using one of several approaches. So then once we have that standard error, we can then construct our confidence intervals. Okay? All right, so in a previous class, we looked at the mean SDMT score in MS patients who were relapsing, and this was shown to have an approximately normal distribution. So to calculate the confidence interval for the mean, we use the t-distribution and the standard deviation from the data. What if instead of the mean SDMT score, we wanted to look at this other measure called the fatigue score? Okay, so now I'm interested in a different measure called the fatigue score, and here's a histogram of what fatigue score looks like. Okay. So what if I simplified this just like we did before and assume that there were only 5, clearly we have more than 5 fatigue scores here in our data set. But suppose we only had 5 fatigue scores available to us, right? And they were 42, 32, 55, 62, and 58. And so for the mean of this data set is 49.8. Then we resample, again, remember, with replacement. And suppose our first one, we get 42, we get 55, we get 62, we get 55 because it's back in the pot, and 32. And the mean for this resample is equal to 49.2. Then we do a second resampling. So now you can see why this is called bootstrapping, right? Because we only have this data available, right? But somehow, with even our small data set, we're picking ourselves up by our bootstraps. That's where the name came from. Where even with a small data set, we're reusing it to get a distribution of means, which is what we're interested in. Okay, so suppose resample 2, I get 55, 58, 32, 58, and 62, for example. And so the mean here is 53. Okay, and then I can do it again. Resample a third time. And say I get 62, 58, 32, 58, and 58. And the mean here would be 53.6. Okay? So now I have 3 resampled means, 49.2, 53, and 53.6. And I can just keep repeating this process, and then I'd get a distribution of means. And then I'd have also, since I have a distribution, I could calculate its standard deviation. Okay? So hopefully you're seeing the idea behind this. So here's my Bootstrap distribution. Whoops. Bootstrap distribution. So what I'm doing is I'm resampling, and then after a given number of resamples, we have a distribution of the resampled statistic. Here, the statistic is the mean. Okay, so I showed you three means we could have calculated. Here are a bunch of means plotted in a histogram. Okay, this is the mean. The distribution of 5,000 resampled means are shown here. Okay, so 5,000. We did 5,000 Bootstrap samples. We got 5,000 different means and then plotted them here. Okay. So now that we have this distribution, we can estimate the standard error using the standard error of the Bootstrap distribution. That's the normal approximation. Okay. So in other words, we're trying to get a standard error, and so we can just go to this distribution and calculate the standard deviation and use that. Alternatively, we can use the 2.5. I don't know exactly where it would fall, but we can use the 2.5%. Whoops. Sorry, this keeps moving. The 2.5% and the 97.5% tiles. We can use the 2.5 and 97.5 percentiles from the Bootstrap distribution. This would be called a percentile Bootstrap distribution. And then there are other ways to do it as well once we have this Bootstrap distribution. But these are ways to use the information from the Bootstrap distribution to then create a confidence interval. Okay, so the point estimate, in other words, remember our confidence intervals always had this form estimate plus or minus t critical value times standard error. The estimate is always the same, right? The estimate isn't changing. What we're talking about here is how to calculate the standard error, right? So, what do these different ones look like in an example? Well, here's what we've been doing. A confidence interval based on the t distribution. That's the first part here. Then we could do a percentile Bootstrap confidence interval. We could do the normal Bootstrap. This is a bias corrected Bootstrap. We're not going to get into the specifics of what that means. Just know that there are different ways, but you can see here the confidence intervals are very, very similar. The differences between them are small. But that should just kind of make you feel comfortable that these bootstrap ones, these three, are very similar to the t-distribution which we'd been using before. Okay? So you might wonder, if they're very similar, why are we introducing new things that are so similar? But we'll answer that question here in a little bit. Okay, so what does this look like in Stata? Okay, so this is the command, Bootstrap, and then these bits tell you that the statistic that we're interested in is the mean. We want to do 5,000 resamples, and we're using the variable called fatigue score, and so on. Okay. Okay, and then Stata then gives us Bootstrap results. Okay, again, we took 5,000 replicates. Looks like there were 252 observations in the data set to begin with. We took 5,000 replicates of that, and then here are the observed means and standard errors and so on, and then the confidence interval based on that. Okay. And so here's, if you ask for this, these other results, you can see there are different ways to construct confidence intervals based on Bootstrap samples. And down here in the legend, it explains the differences. Here's the normal confidence interval. Here's the percentile confidence interval, the bias-corrected confidence interval, and so on. We don't need to worry about all those details, but just know that there are different ways of calculating the confidence intervals based on Bootstrap samples. Okay. Okay, so in this simple example, we've estimated the confidence interval for a mean using the Bootstrap, but the confidence intervals for other statistics can be calculated using the Bootstrap as well. So we might be interested in a confidence interval for the median, for example, or a confidence interval for a ratio between two things or between group differences, okay? So these are statistics for which, remember for the mean we had that really nice result about sigma over root n. But if I were to want to create a confidence interval for the median, I don't have a corresponding sigma over root n, the standard error of the median. I don't know what the standard error of a ratio would be, for example. In those sorts of cases, the Bootstrap is very useful because we can then get estimates of the variability of those statistics. Okay, but again, just a bit of warning that the Bootstrap is a relatively advanced statistical technique, so you shouldn't be doing this on your own. But if it's good to know about it, but it's something that you'll want to consult a statistician about because there are many important questions to answer. The most basic and most important question is, what statistic are you trying to estimate? And then once you know that, how many Bootstrap samples do you need? How should the resampling be done? Which of the Bootstrap confidence intervals should be reported, and so on. Okay. Stata actually provides some nice documentation on this. It's a good place to start, but you should consult a statistician, and that'll keep us in business as well. Just kidding. Okay, so that's the Bootstrap. So hopefully you have a kind of an understanding of why it's a neat idea. We have a small sample, and then even though it's a small sample, we resample from it. We lift ourselves up by the bootstraps, so to speak, and we're able to construct distributions just based on the one sample we have. We have one sample, we resample a bunch of times, and then we create a distribution, and we get a sense for the variability. So it's a very cool idea. Okay, now let's talk about permutation tests. Okay, this is the final non-parametric method that we'll discuss, okay? So the bootstrap is a non-parametric. There's no distribution assumed, right, when we resample our data. And similarly, the permutation tests are also non-parametric, okay? So in permutation tests, they're similar to the bootstrap because we choose a statistic that is going to measure an effect of interest. We then permute the data labels to calculate an exact p-value. Okay, so don't worry if that doesn't make sense now. It'll make more sense in an example. Okay, so remember we wanted to suppose we want to compare the mean fatigue score in two groups of mice, group A versus group B. Okay, so we want to compare mean fatigue score in two groups of mice. A and B. Okay? And suppose fatigue is measured on a 0 to 10 scale. Not exactly sure how we're figuring out how fatigued mice are, but suppose it's possible for us to measure. I guess the mice talk to us and tell us how tired they are. But anyway, this is just an example, so we're not too worried about it. Okay, so suppose here's our data. Okay, and we have 3 mice in each group, and suppose in group A, the fatigue scores are 5, 7, and 8, so that the mean is 6.67. And then in group B, suppose the fatigue scores are 3, 4, and 6, so that the mean fatigue score is equal to 4.33. Okay? And so the observed difference between the means is going to be 2.34. Okay? That's the observed difference in means. If you just take 6.67, subtract 4.33, you get 2.34. Okay, that's our observed difference in means. Okay, so now we want to move to hypothesis testing, right? We know that the observed difference is 2.34, but the next question for us is this a significant difference? Is this a meaningful difference, or is it just due to chance? Okay, so if we were going to go the t-test route, which is what we've learned up to now, we would start with the null hypothesis that the mean in group, the population mean in group A is equal to the mean in group B. Okay, and this assumes that the underlying distribution is normal, but again, we only have 3 mice in each of group A and in group B, so it might be hard for us to justify the normality assumption. Okay, instead of this null hypothesis, so this is the null hypothesis that corresponds to a t-test. Okay, And obviously this would be a 2-sample t-test because there's group A and group B. Okay, so an alternative null hypothesis would be that the distributions in group A is equal to the distribution in group B. Okay? And since we haven't specified what kind of distribution this is non-parametric, right? This is a non-parametric hypothesis. Okay? So how would we calculate the p-value? We know how to calculate the p-value in this case, in the t-test. We've done it several times now. How would we calculate the p-value here in the non-parametric test? Okay, so again, remember what a p-value is. It's the probability of the observed result or something more extreme under the null hypothesis. Okay, so under the null, the two groups are the same. Okay, so to calculate a p-value, we can calculate the possible mean differences if the group labels were to change. By group labels, we mean which mice are in group A and which mice are in group B. So in other words, if we randomly permute the group labels, we can construct a distribution of differences. And so now hopefully you're getting an understanding of why this is called a permutation test, right? We had 6 data points before. Let me just write those out again. We had 6 data points. We had A, group A had 5 fatigue scores of 5, 7, and 8. And group B had fatigue scores of 3, 4, and 6. If I permute these labels and resample, then I can construct a p-value. So let me show you an example of what that means. Whoops. Okay, this didn't turn out the way I was hoping, but that's okay. We can write it out. So again, in group A we had the numbers 5, 7, and 8, and in group B we had the numbers 3, 4, and 6. Okay, so what are the possible permutations of this? Okay, so we could write all of these out. So we could have set, and then we'd have group A, and we'd have group B, and then we'd have the mean difference. Okay? So in set 1, for example, so what are we doing? We're taking these 6 numbers, 5, 7, 8, and 3, 4, and 6, and just switching around which group they belong to, okay? So we could say that group A actually has 3, 4, and 5, and group B has 6, 7, and 8, and in that case, the mean difference between them would be -3. That's set 1. In set 2, we could say that group A actually has 3, 4, and 6, and that group B has 5, 7, and 8, and the mean difference would be -2.33. And then we'd go to the third set and say, let's say 3, 4, and 7 are in group A, and 5, 6, and 8 are in group B. And the mean difference would be 1.67. Okay? And so on. We could just keep repeating this process all the way down. It turns out for this case where we have 6 different numbers, there are only 20 possible permutations, okay? And so remember that the mean difference that we have for our actual data, the mean difference was 2.33, because we know that the mean here is, or 2.34. The mean here is 6.67, and the mean here is 4.33. 4.33. Okay. And so the mean difference that we have for our data was 2.34. So again, we can permute the labels, and then it turns out again that there are 20 different combinations in this case, and we can write them all out, but I won't write them all here. Okay, and then the final one is 6, 7, and 8, and 3, 4, and 5 for a mean difference of 3. Okay, so you can see now, if we again recall the definition of a p-value, the probability of observing something as or more extreme than the observed result. The observed result was a mean difference of 2.34. So the probability of observing something as or more extreme here was, out of the 20 possibilities, 2 of them had results as, so this is as extreme, our case. Here's something more extreme, right? A mean difference of 3. So that means there are 2 possible values out of the 20 that are as or more extreme than the observed result. So that means our one-sided p-value in this case is 2 out of 20, or 0.1. Okay, and if we wanted to make this a two-sided p-value, we simply multiply by 2, so that the two-sided p-value is equal to 0.20. Okay, so you see how we did that. It was simple in this case, where we only had 6 numbers, 6 data points. We just said, hey, we know that in our actual data set 5, 7, and 8 belong to group A, and 3, 4, and 6 belong to group B. But if we mix those around and mixed which groups they belong to, we can mix them in 20 different ways, which is what we listed here. And then we said which ones of those lead to the statistic of interest, the mean difference, being as or more extreme than the observed result. The observed result was a mean difference of 2.34. There was only one that was as extreme, and then there was one that was more extreme. And that gave us our one-sided p-value, 0.1. We multiplied it by 2 to get the two-sided p-value, 0.2. Okay, so if we were to go through all of our steps of hypothesis testing, again, the null hypothesis here would be, I'm not going to write this all out, but the null hypothesis here involves the distribution. That's why we write this capital F for the CDF, or the cumulative distribution function. Distribution in group A is equal to the distribution in group B. Okay, and then the type of data that we have is a continuous outcome with a dichotomous predictor. Okay, we're using a permutation test. Our test statistic is a mean difference between the two groups equal to 2.34. Then we calculate a p-value based on our permutation test. Remember, we said our two-sided p-value was 0.20. Since 0.20 is greater than 0.05, we fail to reject. And then we conclude that based on our sample, there is no significant difference between group A and B. Okay. So using the same concept, so hopefully that makes sense, as a permutation test, we're able to write out all the possibilities. Okay. All right. So remember we had talked about the Wilcoxon signed rank test, and we'd use a normal approximation to calculate the p-value. Well, it turns out we can do an exact Wilcoxon test as well. So what do we mean by that? Remember we had these pairs. We had the patient and the matched control, and then a difference, and then we calculated the rank, right? So we can calculate a p-value from the exact Wilcoxon signed rank test using, a permutation test. The statistic of interest here is the sum of the positive ranks. So this one is negative, and this one is negative. So the sum of the positive ranks were this one and all of these guys. And then we can use a permutation test. So that means we're going to permute which one is the patient and which one is the control, and we can get a distribution. Okay. Okay. So under the null hypothesis, half of the ranks should be positive and half should be negative. And then to find the exact p-value, the different possible sum of positive ranks are calculated, and then we can write those all out. So in our previous example, it was nice because there were only 20 possibilities, but you can see how the number of possibilities would grow exponentially. Okay, so if we look at the sum of the positive ranks, that's what we're interested in. We can see, so the sum of the positive ranks, if it were to be 0, for example, we know that all the ranks are negative. This happens 1 out of 1,024 times. If the sum of the ranks were 1, only rank 1 is positive. This happens 1 out of 1,024 times, and so on. So we can write out all of these different probabilities for these different sum of positive ranks, and then use that to calculate the exact p-value. So we simply count the number of ways we could observe our situation or something more extreme, the definition of a p-value, and then we use that to get at the result that we're interested in. Okay? Okay. So in many cases, you can see here there were 55 possibilities. In many cases, if we have larger sample sizes, we can't enumerate all of the permutations to calculate an exact p-value. Okay, and so the permute command in Stata does an approximation by performing a set number of permutations to calculate the distribution of a test statistic. And again, here is where you might consider consulting a statistician, because we're lonely and you should come talk to us. Okay, so conclusions: the Bootstrap and permutation tests are approaches based on resampling to calculate confidence intervals and p-values. Okay, these approaches make fewer assumptions about the distribution of the data, but they're more advanced and should be used after consultation with a statistician. So hopefully the basic ideas, the point here is to just understand the basic idea. So by resampling the data that we have, the data we have is a sample, hopefully, from the population, right? We have data that's a sample from the population, but then we resample our own data, and by doing so, in the Bootstrap setting, we can then calculate confidence intervals, and then in the permutation setting, by switching kind of the labels, we know which mice are in group A and which mice are in group B, but if we suppose that we could mix them all up in all possible different ways, we can then calculate exact p-values. So kind of neat ideas that we use often in statistics. Okay, so again, that's just a very gentle introduction to bootstrapping and permutation tests. Lots more technical details in there that you should talk to a statistician about. Okay, I will stop there and see you in the next session.